Hello students, welcome back. I have retained the part of the earlier diagram. In the previous video, this diagram was there and I have retained that. Now what I want to do here, I want you to remember a few things. What we have done here, we have considered a source which was of infinite heat capacity. Meaning what? It means you were transferring heat from this to Carnot engine, but the temperature of this was constant, right? It was not changing. That means this source is of infinite heat capacity. So if there is a source, that's the definition of source. It's a conceptual thing. So if no matter how much heat you take from it, its temperature will not drop. Okay, so that's the concept of source. Similarly, sink is the surrounding temperature, right? And whatever amount of heat you give, sink is this temperature. The temperature of the surrounding is not going to change, it will not increase because you are adding some heat, but its surrounding is a big thing. So sink temperature will also constant. So it was infinite heat capacity source, right? This is a source of infinite heat capacity. Now I want to take a practical example. That means in practice, any body which is giving the heat, its temperature, as soon as it starts giving heat, it will drop, right? Except in the case when there is phase transformation. Suppose steam is condensing, right? Then although steam is giving heat, but its temperature is not going to drop. It will be constant temperature, phase transformation. But leave it aside and let's take an example. Let's say that we have a certain fluid, okay, and that fluid, or say fluid means liquid or gas, let's say more specific, let's say gas, okay, and we have certain gas coming from a combustion chamber, and that the gas temperature is say 1100 degrees Celsius, okay, 1100 degrees Celsius. If you just add 273 12 Kelvin, so I can say it is 1273, okay, so 1273 Kelvin. Surrounding is, let's say, it is at 290, but now we have gas. This is gas, okay, and it is at 1273 Kelvin. Now look at this. This was a source we considered of 1000 Kelvin, but its temperature was always constant, no matter how much heat you extracted. But this is not that. The moment you start giving out, now you want to find out if there is certain amount of heat coming from out of it, right? Let's say, so heat is flowing out of this. So this heat, how much is the available energy? Let's say that we drop the temperature of this gas. That means we are taking out heat, and the total, as a result, the temperature of the gas keeps on dropping. And let's say that temperature of the gas drops to say 500 Kelvin, okay, 500 Kelvin. That means how much heat has flown from the gas? How much heat has flown from the gas? That will be Q will be mass of the gas, Cp of the gas, right? Cp of the gas into delta T, right? Into delta T. That is drop in temperature. How much temperature has dropped? So we can say it is 1273 minus 500. Okay, that's the change in. So this is the amount of heat that will come from the gas. Now, if you want to find out, how much of that is, this is how much of that is available energy, right? How much of that is available energy? That's your question. Then what you have to do? You have to, this heat, we have to imagine that this heat is given to Carnot engine, and you run a Carnot engine, and then you find out the work, okay? That's the thing. But suppose in second case, what we do, like here, instead of giving it to Carnot engine, we transferred it to, first the gas gave the heat to some other fluid, okay, and that fluid, let's say it was at a lower temperature. Like here, it was T here, T dash here. Similarly, here we are considering this gas is giving this heat to some other fluid which is at a lower temperature, right? Which is at a lower temperature. Then and then from there, right? Let's say the gas is giving the fluid at a lower temperature, and that low temperature fluid is, let's say, at 400 Kelvin. Okay. So heat is given to that, and from there, if you run the Karma engines and then find out available energy. So now we are asked, how much will be drop in available energy if the gas gave the heat irreversibly to some other fluid which was at a lower temperature 400, okay, which was at lower temperature 400. Now I want you to recollect the point which I made in the previous video. I said that decrease in available energy, decrease in was equal to T0, which is the sink temperature, into delta S dash minus delta S. Delta S dash minus delta S. Now see here, how you have to, all that you have to find out, because your sink temperature is given to you. You have to find out delta S dash and delta S. Now the question is, how will you find out delta S dash and delta S? Now just understand this. So I am considering gas flowing in a heat exchanger. Initial temperature is T1. It is giving heat to some other fluid. Okay. Suppose the gas is flowing like this, and I consider some other fluid which is flowing from T1 dash to T2 dash. That means it is flowing in this direction. Please note, gas must be at a higher temperature than this fluid. So this is gas and there is some fluid. This fluid could be liquid or gas, whatever. So this gas will cool because it is giving the heat. This is Q, right? This gas will cool. This fluid will be heated. Now look at what will the entropy change of this. What will be the entropy change of this? Entropy change, you know that if the temperature is changing from T1 to T2, entropy change, let's say delta S, is equal to M of this gas, M dot, let's say mass flow rate, Cp of this gas, right? Ln natural law, T2 by T1. What is T2? T2 is the temperature of the gas after it has given the heat, and T1 is the temperature of the gas before it has started giving the heat. So it is T2 by T1. It is T2 by T1. Now this is the fluid to which heat is given, and this is irreversible heat transfer. This is irreversible heat transfer. So here you can see that the heat given by this gas is exactly equal to heat received by this. There is no energy is conserved. But what has happened is, now when you give the heat to this fluid, now its entropy is going to increase, and that entropy change we can say is delta S dash, right? That is delta S dash. So how much will be delta S dash? You can, then the equation is, because temperature is rising from T1 dash to T2 dash, I can write this as m dot F, that is some fluid, it could be liquid or gas, m dot F Cpf Ln, final temperature is T2 dash, initial temperature is T1 dash. Okay. Now see, if you compare these two, you can immediately see that, see, here this is going to decrease because this will be with negative sign. Why? Because entropy is decreasing. This will be with positive sign, because entropy here of this is increasing. This is leaving this body or this gas is giving out heat, so its entropy will decrease. This gas will this fluid will receive the heat, so its entropy is increased. Now, but if you forgetting the signs, if you find out the values, these two values, you will see that this value delta S dash, forget the sign, will be higher than this. Okay, will be higher than this. Why? Because there is, you should recollect that when there is irreversible heat transfer from a body at high temperature to body at low temperature, then if you consider these two bodies as an isolated system, principle of increase of entropy says that when you have an isolated system and if there is an irreversible process, which is a irreversible heat transfer here, entropy of this isolated system will increase. Principle of increase of entropy or entropy principle. Please watch the video. Okay. So here, when heat is transferred irreversibly, entropy of this will decrease, but entropy of this, of course, will increase. But the increase will be more than decrease. If this entropy is if entropy decreases by 5 units, any value, then this entropy increase will be more than 5, to be 6, 7, 8, whatever, right? So that means because of this irreversible heat transfer, there is extra entropy generated. So if you do the algebraic sum of this, that will be positive, okay? And this is what is here. This delta S dash minus delta S is the entropy generation in the universe because of this irreversible heat transfer. Because of irreversible heat transfer. If this heat were directly given to Carnot engine and you produced work, right, that would have been some available energy. But now this heat is coming to this fluid. This fluid now will give heat to Carnot engine and you will get work. That work will be less. And that difference is decrease in available energy. So if in the numericals, the central point is, if you are told that, if you are given any two objects, any two substances, there could be gas, fluid, solids, whatever. One is giving the heat, other is receiving the heat. Then it is an irreversible heat transfer. So this heat is losing its capacity to get transformed into work. That means there will be decrease in available energy, which you can find out by separately finding out entropy change. Okay? By separately finding out entropy change and adding it algebraically, you will get this term. You will get this term into T0. T0 is your lowest temperature, the sink temperature. So T0 into delta S dash minus delta S. This will give you decrease in available energy. I would speak more about this, but at the moment, please understand and remember the term, every term, delta S dash, delta S T0. This is the expression you would like to remember. You will surely get a numerical in exams and you want to solve them. You can solve them in quickly. All the numericals in available energy chapter will be solved, can be solved very quickly. It's a conceptual thing, but once you understand the concept, you can quickly score.